Hello and welcome to this next part of our inorganic chemistry of coordination complexes, where we're going to be talking about magnetism. So this is going to be primarily the magnetism of the D block complexes that we are interested in this course, and just discuss some of their properties, and then how that maybe will lead us on to the foundation of some of the earlier, the foundational structural theories of coordination complexes. So a little bit of a summary, I guess, of some of the terms that we'll use. So in magnetism, so diamagnetism is our molecules containing a closed shell of electrons when placed in a magnetic field act in a manner akin to Lenz's law, namely a small current can be considered to be generated, which opposes the applied magnetic field. So molecules with closed shells are therefore weakly repelled by a magnetic field, and so these are said to be diamagnetic. Effects of diamagnetism are approximately additive for each atom present, so we can use tables of such diamagnetic constants to allow for each type of atom or functional group, and hence deduce total diamagnetism of a particular compound. Paramagnetism, on the other hand, is whenever we have a molecule containing more than one unpaired electron, and there is a magnetic field associated with this spinning electron, such that the molecule will be attracted into the magnetic field, and so both spin and orbital motions of the electron contribute to this field. So in reality, how this sort of manifests itself is that paramagnetism is a great deal more influential and much stronger than diamagnetism. So transition metals typically have unpaired electrons. That was sort of one of our early definitions, was this idea that they would have some sort of like, they wouldn't have a completely filled D shell. So we must remember also Hund's rules that electrons occupy separate orbitals with their spins being parallel if they're in the different orbitals. This, for example, titanium 2+, it's a D2 complex. We filled up two orbitals, half filled them, so we've got two unpaired electrons with their spins pointing in the same direction. Now, it could have been up, could have been down. It's rather arbitrary, so long as we know that they are parallel to each other. This would give us then two unpaired electrons. Vanadium 2+ is D3, and so it fills up, according to Hund's rules, 3 out of 5 of the d orbitals, and it says then that we have 3 unpaired electrons. Chromium 2+, D4, it's got something similar. It's 4 unpaired electrons, and so on. Manganese 2+ is D5, 5 unpaired electrons. Then, of course, when we get to D6, we now start to have to pair our electrons in orbitals, and so on and so forth, until such times as we come to zinc 2+, which has a completely filled D set of d orbitals, which I suppose means that it's not really a transition metal according to our definition that we had established in the first part of the series. And so this would no longer show any paramagnetism, and it would be diamagnetic, whereas the rest with their unpaired electrons would be showing paramagnetism. So of course, how do you measure this? So one of the ways is using a Gauss balance. This is for recording magnetic susceptibility. So what you have is you have a balance, and then you have your sample, which is sort of suspended between two magnets. Then we record the mass change whenever the magnetic field is turned on, or whenever the sample is placed between the inside the magnetic field. So place the sample between two poles of the magnetic field, and then record the mass. Turn on the magnetic field. Generally, it's an electromagnet. And then if it is repelled by the field, then it's going to be diamagnetic. Diamagnetism, typically there's no unpaired electrons, and the atom will generate an opposing electric field against the magnetic field. And so what you will see is that it will push the sample up, and so this will reduce the mass. It will repel it. However, if it is paramagnetic, i.e. it has some unpaired electrons, then it will be pulled into the electric field, because the electrons will align with the electric field, and so will in some way enhance the magnetic field. There's also, of course, this is important to realize, is that just because something's paramagnetic doesn't mean that it's not also diamagnetic. There can also be diamagnetic contributions, but these are much smaller than those of paramagnetic contributions. So from this change in weight, we're able to determine something called the magnetic susceptibility. And so this would be, for a sample, called the magnetic susceptibility, or this letter chi probably overused in chemistry. So calculate the molar magnetic susceptibility, chi m, which has units of cubic centimeters per mole. And sometimes we see this corrected as chi m, where the diamagnetic contribution has been removed. So sometimes there's a corrected chi m, which has had the diamagnetic contribution from any elements in the complex which do not have unpaired electrons. Then from this chi m, we can calculate the magnetic moment. So we calculate an experimental value for the magnetic moment, which we term mu, which has got units of Bm, or Bohr magnetrons. And so this is the equation to get the magnetic moment from the magnetic susceptibility. Here, N, R, and T are all, well, T is the temperature, N and R are constants. And so that means that if we know the magnetic susceptibility, we can determine the magnetic moment. And so since we can fill in the values of N and R, and then we'll end up getting this term here, where we have the magnetic moment is equal to the square root of 2.83 times the magnetic susceptibility times T, the temperature. So the magnetic moment is going to be temperature dependent. So we can estimate a theoretical value for mu based on the number of unpaired electrons. So our first approximation is made by taking into account only the spin contributions of unpaired electrons. So theoretical magnetic moment is equal to the square root of n times n plus 2, where n is the number of unpaired electrons present, and mu is, of course, the magnetic moment in Bohr magnetrons. So the experimental magnetic moments are often slightly higher than that predicted by this spin-only formula because of the orbital motion contribution. This is just really a very rough guide. And so, I mean, if you could do this calculation very quickly once you know the number of unpaired electrons, and that would give you a guide as to what sort of value you should be obtaining from this equation after you've measured the magnetic susceptibility. So some textbooks give what appears to be a different formula, which uses the spin s and not the number of unpaired electrons. So in this case, the spin is, of course, either plus a half or minus a half. This is the spin quantum number. So it's really just multiplied by 2 or plus 1, as opposed to, it gives you effectively the same value. So these two forms of the same approximation equation. Here we have a number of different transition metal ions. Their number of d electrons, unpaired electrons, has been shown here, and then the d electron count, and then the calculated magnetic moment using that equation on the previous slide, and then our observed magnetic moment here. So, for example, in vanadium 4+, we have vanadium is usually d5, because vanadium 0, so it has lost 4 electrons. So it is only d1. So we put that into our equation. The mu is equal to the square root of n plus 2, or times n plus 2. It would give us a value of 1.73. And then we find out that the observed moment is somewhere between 1.7 and 1.8. So very, very close. Generally, they are quite accurate. Usually, the values of the observed moment might be a little bit higher. Sometimes, yeah. So, like for example, the cobalt 3+ here, it's significantly higher. But there are some instances where, for example, down here, I want to draw your attention to the idea that if we have 0 unpaired electrons, then we're not going to have any calculated magnetic moment, since we're only going to have diamagnetism. And so we also see that that is also capable of calculating accurately the observed moment. So how do we explain why iron 2+, this one, can have 0 unpaired electrons, and why can nickel 2+ here have 0 unpaired electrons as well? So this is, so we also see here, this is D5, but it only has 3 unpaired electrons. Why is that? We have 5 d orbitals, so how can we only have 3 unpaired electrons? And so ultimately, this is sort of like the magnetism part, where we think we know how many unpaired electrons we have, and then we do the calculation of the magnetic moment, and then we find out the observed moment is really quite different, is a result of sort of interesting behavior of these transition metal complexes whenever they form complexes. These are all gas phase ions, and so that's why they're able to have, they have degenerate d orbitals, which all have the same energy. So we're given an observed value of the effective magnetic moment for this chromium complex. Is going to be 4.75 Bohr magnetons. So we've got to, we're asked to deduce the number of unpaired electrons. So we know what mu is equal to. It's equal to 4.75, and that's equal to the square root of n times n plus 1, or plus 2, sorry. So the this complex we would assume is octahedral, since it's got 3 bidentate ligands. These ethylene are 1,2 ethylene diamine. The oxidation state of chromium is 2+, since these are neutral ligands. It means that the 2+ comes from the chromium, and so that means that since chromium is, well, chromium metal would have 60 electrons. If it's lost 2 to be the 2+ ion, then it will have 4 electrons, and so that means we can try to calculate the number of unpaired electrons. Now, if we said we had d4 electrons with 5 d orbitals, we might be tempted to say that we have 4 unpaired electrons. Simply because following Hund's rule, we would half fill each orbital before fully filling. So we'll guess that n is probably equal to 4, and then we would calculate that we get the theoretical magnetic moment of 4.9, which is pretty close to 4.75. So we assume that there are going to be 4 unpaired electrons in the complex. So we need some type of bonding model for coordination complexes to explain not only these kind of unusual magnetic moments that we saw, but also why some complexes are different colors, even though they have the same metal. You know, if there was no sort of like strange, or not strange, but unique behavior going on, then we would assume that these 2 copper complexes would be the same color. This octahedral complex, copper complex is blue, and then this tetrahedral copper complex is green, but yet the oxidation state of copper in both is +2. And we also ask why we have different bonding geometries. So for example, this tetracarbonyl nickel 0 is tetrahedral, but this tetrachloroplatinate is platinate 2 is in fact square planar. So why do we get these structures? You know, they both are, they don't have any lone pairs on the central atom. There's they both have 4 electron domains, so their electron domain geometry should be the same. And so this would be where valence shell electron pair repulsion theory really starts to break down and does not really predict the shape of transition metal complexes very well at all. This of course led to, you know, these experimental observations led to a lot of consternation amongst coordination chemists and chemists in general as to what was going on. Why were they getting these results, which they couldn't really explain using the theories that they had. And so they tried to apply different theories to these complexes. So one of the theories they tried to apply was valence bond theory. So in the 1930s, this was done by Linus Pauling, and used the basis of the hybridization model. So maybe the hybridization model can try to explain why we have different octahedral complexes, tetrahedral complexes, square planar complexes, and so on. Then that proved okay, but it wasn't very good. So Another theory was developed, this crystal field theory, which was proposed by Bethe and Van Vliet. It was generally not accepted until the 1950s, primarily because it was kind of developed for geologists to try and explain the bonding in gemstones, and the valence bond theory seemed to work okay. And since that had been developed by chemists, they kind of stuck to their own theories. But around about the 1950s, in an explosion of sort of modern chemistry, this theory, this crystal field theory, and its later adoption, although it came out around about the same time, ligand field theory was developed. And so these theories are still valid today. Actually, some theories have been developed since then, but by and large, crystal field and ligand field theory very well describe the bonding and the properties of transition metals that we see. Molecular orbital theory, of course, we've had that before. So this was first introduced in the 1960s and generally taken as the modern method of predicting the structure, magnetism, and spectral characteristics of transition metal coordination complexes. The problem with molecular orbital theory is that it gets very complicated very quickly with transition metals. And so the combination of molecular orbital theory with crystal field theory is how we came up with ligand field theory. The combination of these two theories allows us to really understand what we're seeing with transition metals. So let's talk about how valence bond theory could be applied to our complexes. So this was applied by Linus Pauling, of course. So if we have different coordination numbers, we have different shapes. Just a little revision. So we've got coordination number 2, we have sp hybridization. We're combining an s orbital with a p orbital to get a linear complex. If we have coordination number 4, one of the potentials is sp3 tetrahedral. To get coordination number 4, we would need to have, for a square planar complex, sorry, we would need to have sp2d hybridization, and then just the different hybridization models that would work for different complexes. Valence bond theory, however, is seriously flawed. It kind of works okay for S and P block elements. You're talking about your carbons, your nitrogens, even your sulfurs and your phosphorus. Kind of works okay. Not as good, obviously, as molecular orbital theory, but it's gives you a result quicker, I suppose. Secondly, from a symmetry point of view, orbitals cannot mix. Quantum mechanics forbids it. Yeah, it's really just a crutch to trying to understand the structures. We can't like take part of one orbital and combine it with another part of a different orbital. Orbitals don't do that. So it does not always explain the structure, and fails to give an explanation of the color of complexes. It fails to explain bonding to certain types of ligands, such as carbonyls. Okay, and so that will lead us on then to the next part, which is going to be where we talk about crystal field theory in a lot more detail.